everyone. My name is Alessandro Rossetta. I am the CEO and founder of flimlabs. And in today's webinar, we're going to give you an overview of what is achievable using our constant fraction discriminator. Okay, so here we go. So basically, we're going to take a look on how to configure and use our constant fraction discriminator. First of all, what is a constant fraction discriminator? Well, it's an electronic device that generates precise and accurate digital timestamps for input signals with varying amplitude, but a consistent rise time. What I mean with this, basically, we have an input. There is a voltage input that basically has an amplitude that changes over time, but has always a constant rise time. And thanks to our CFD, we can process this signal and transform this into a digital version where the input signal keeps the alignment in time between the input and the output. Let's see a quick video to demo this behavior. So here is basically a video that shows an input that you see, it's basically changing its amplitude, and then the output of the constant fraction discriminator makes it digital with a constant rise time. And this is basically the idea of a constant fraction discriminator. Let's continue on in today's presentation, presenting you our constant fraction discriminator. Here you see it in three different views. From the top, on the side, and in one of the two sides. And what to say about this? First of all, that it's very compact. As you can see, the dimensions are very, very tiny. And it's portable because it is powered, could be powered through a USB-C cable, a USB-C Type-C cable, eventually using also a battery pack. Then, continuing on the discussion and to explain you the feature of our CFD, if you see in the case, it's equipped with some mounting holes for allowing the constant fraction discriminator to be bolted down on optical tables. And then if we make, let's say, a comparison to what is available on the market, our CFD is the only, I would say, single channel CFD module on the market, because here you see some other constant fraction discriminators, which are, for example, 16 channels, 4 channel, and 4 channels. And what we can tell, besides the fact that they have more channels, so they are not a single channel element, a single channel module, is that they need to be mounted on a specific rack, and most importantly, they cannot be powered using a USB cable. So let me give you a more technical detail and overview on what is, let's say, the working principle of a constant fraction discriminator. So as I told you, we basically, the CFD basically accepts an input signal. There is a voltage signal with a specific amplitude. Then whenever the signal, as soon as the signal enters the constant fraction discriminator, it gets duplicated. So we make a copy of the same signal, and these two copies are identical. Then one of the two copies gets inverted, meaning that we invert its polarity internally in the CFD, and then the copy that was not inverted gets delayed. And we'll see in a bit how we can delay and what are we using for delaying the signal. So basically now we would have two identical copies of the same signal, but one of the two is inverted and the other one is a little bit delayed, so it's shifted in time. At this moment, the inner circuit of the CFD basically adds the two signals together, so sum them up, so that we basically have a signal with this shape. And such a signal is then fed to a digital flip-flop that basically will be triggered and will see the changing in polarity, the zero crossing, that's how it's called, the zero crossing part of the signal. So basically, you see this signal is going negative and then positive, and the moment the signal cross the zero line, so the zero amplitude, then it gets detected by the digital flip-flop, and then a digital signal will be, let's say, triggered out and will be sent out. So this is a block schematic telling you what the CFD does. And again, the overall and the main function of the CFD is to take a voltage signal with a changing amplitude as an input and give as output a digital copy, which basically keeps and retains the arrival time and the rise time of the input signal. If we look at the main features of our constant fraction discriminator, we first can say that it has a power good light. So after you power the CFD, if the LED of the power good light doesn't come on, then we have a problem. So this is a first way to troubleshoot eventually the constant fraction discriminator. And then if we move on into, let's say, describing what are the other connections in our constant fraction discriminator, you see that we have an input port, which is a SMA port. And here is where we actually connect the input signal. Then another, let's say, feature of our CFD is that you can trim the input threshold level. So basically, thanks to a little screwdriver that we also provide in the package of the constant fraction discriminator, we can adjust the input threshold level, and this will, for example, allow us to select the minimum voltage of the input signal that the CFD can actually detect. So for example, if the threshold level is low, this means that both of these red signal will be seen by the detector, by the CFD. Otherwise, for example, if we play with a trimmer, we can basically raise the threshold and allow only for one signal or a specific voltage to pass through and to be detected and to be discriminated by the CFD. How do we do this? Well, we need to play with a screwdriver using the potentiometer, while at the same time connecting the terminals of a multimeter, of a voltmeter, to the test point, and basically measure, while we twist the potentiometer screw, what is the actual voltage level. So what is the actual input threshold level. We want to do this measurement keeping the multimeter in the millivolt range, in the millivolt scale. Then, as I mentioned before, for accomplishing the discriminations of changing of input signal with changing amplitude and to transform them into a digital copy, we need to delay internally the signal. Well, we at flimlabs, we designed our constant fraction discriminator with a physical delay line that we provide also together with the constant fraction discriminator module. And basically, this delay line has to be, let's say, sorry, there is an error in the slides. Here we say the polarity switch, but should be the delay line. So here, basically, we connect a cable into these two connectors of a delay line, a physical cable, and this allows for the signal to be delayed. With the bigger aim of delaying the signal for accomplishing the digital discrimination. That's what I meant. So basically, we can connect a coaxial cable based on the rising edge of the input signal. So for example, if we have an input signal with a varying amplitude that has a rising time of about 1 nanosecond, then the rule of thumb that we would apply would tell us to use a 30 centimeter long delay cable. Another feature of our constant fraction discriminator is the possibility and the capability for this CFD to deal both with positive and negative input polarity signals. This means that, for example, if we need to digitally discriminate an input coming from a photomultiplier tube, which usually is a negative, then we can, of course, use the CFD by changing the polarity switch to negative. On the other hand, if we are dealing with a signal that is positive, for example, coming from a photodiode or from a laser sync signal, we can basically put the switch in the other direction and deal with a polarity, a positive polarity signal. If we take a closer look at all the output signals and output connectors, you'll see that we have two connectors for SMA, meaning that the CFD is capable of outputting two identical copies of the signal that gets discriminated in the SMA LVTTL type. And also we equip it with type C connectors for giving as output also LVDS type of signal, which I'll tell you in a bit. So the idea, if we take, let's say, overall perspective of what is capable to do and the capabilities of our CFD, the idea is that we can deal both with positive and negative signals, and then we can discriminate using the internal circuit of the CFD, and the CFD will give us output four outputs, two identical copies of the LVTTL signal on the SMA connectors. And as I said a few seconds ago, we can also have the same signal on the LVDS, with LVDS type over a USB Type-C port. Why so? Because these signals can be directly connected with our proprietary data sharing protocol, let's say, data connection protocol, because we can use the FLIM data acquisition card and connect the USB Type-C LVDS signal to the FLIM data acquisition card to make things easier for the user. Another, let's say, feature that it's worth to talk about when, let's say, talking about the CFD is the possibility throughout always a dedicated potentiometer to regulate the duration of the output signal, so the pulse width of our output signal. Always using a screwdriver and now connecting one of the two outputs with oscilloscope, we can basically play with the screwdriver and with the trimmer to eventually, let's say, make the pulse width longer or shorter, so change the duration of the pulse out. Just to give you a recap on what are the main specifications of the CFD, we can deal with positive and negative input signal. The rise time of the output signal is less than 500 picoseconds with less than 15 picoseconds jitter. The maximum repetition rate the CFD can handle as an input signal is roughly 140 megahertz, is a USB Type-C power device, and the dimensions are very compact. And most importantly, is a single channel module. So what's in our package? So what's in the CFD package? You'll find, of course, the CFD. Then we are going to provide a little screwdriver so that it basically fits the dimension of the screw already. Then we'll provide a USB-A to USB Type-C power cable, as you see here, and also a delay line, 15 centimeter and 30 centimeters long. Here you see just one version of it. Okay, so now what can we use the CFD for? We have two most common use cases. One of them is the laser sync pulse shaping. So we're gonna change the shape of the laser sync coming, for example, from an external laser source. And we can use the CFD for transforming the signal of a Hamamatsu PMT, for example, into a digital version, so into a photon counting type of signal. The laser sync shaping could be trivial, but the idea is that we take the laser source sync, either negative, positive, or coming from a photodiode, and we can transform it into a LVTTL type of signal at 2.5 volts over 50 ohm load. And one direct use case is the digital limb sync discrimination for the PI imaging spuds. So you see we have these two spuds and they can work with a LVTL with a specific output pulse duration. And our CFD is mostly used in conjunction with the two spud for accomplishing, let's say, the discrimination of the laser sync so that the PI imaging spud can correctly see the laser sync. And then the second application that it's worth to mention is the discrimination, the constant fraction discrimination of a signal coming from a sensor or detector, most likely a photomultiplier. Why I'm saying so? Because one of the common application and the most used application the constant fraction discriminator can be used for is to take the signal from a photomultiplier tube and transform it into a digital version so that, for example, a time tagger or our time tagger can directly process it. Here I am showing just, like overall configuration of a two-photon microscope. Here we have the Broker Ultima, for which we provide a FLIM upgrade. And here you can see the constant fraction discriminator used for digitally discriminating the photomultiplier, but also for shaping the laser sync coming, for example, from a MITAI Deep Sea Spectra Physics two-photon source. The constant fraction discriminator works well with our other accessories, which are the active splitter and wideband amplifier. But now, let's say we have a hands-on session together with our senior hardware engineer, Enrico Lenzi, which is with me today in our lab, and you'll see in a bit. And we're gonna basically have a hands-on session with a live demo, and we'll go over, let's say, how to adjust the input threshold of the CFD, and how to connect the CFD with a photomultiplier tube for a TCSPC application. We'll show you also how to adjust the pulse duration of the output. I hope you can still hear me, but you can see our setup. So here we basically built a setup for this webinar. And here I am with Enrico, which you'll see only his hands. Enrico, you can show, let's say, our viewers that we have a cuvette holder with a cuvette with some fluorescent material. Here we connected a photomultiplier tube, and then the photomultiplier tube is connected with an amplifier, our low noise amplifier. And then if we move, let's say, we can give you an overall view of the setup that we prepare for this live demonstration. So here we have our constant fraction discriminator. You see we are powering it through a USB-C cord. Now Enrico can help me out in powering the constant fraction, the multimeter. So we need to see basically the multimeter. And now what we could do is on this side, I am using the two terminals of the multimeter, and I am putting them inside the test points, 1 and 2. And with a screwdriver, we are gonna basically play with the threshold level, and you see it's changing on the screen on the constant fraction discriminator, of the multimeter, I'm sorry. I hope you see that we are twisting the screw and the value on the multimeter is changing. So that's how it is done. Then something that we can also play with, as I was saying, we have another potentiometer in the back, which is the pulse duration. We can remove them. I mean, we're done with this part. So you see here that we have the pulse length, the potentiometer, and you see that the moment I am twisting this potentiometer, there is an oscilloscope signal in the background that maybe Enrico can show you, why I can indicate to you. what I am doing. You see, I am twisting this trimmer so that I can change the pulse duration. So now what I would do, so the cuvette is connected, the cuvette holder, we have a fluorescence filter, then we have a photomultiplier tube, and we are shining a flimlabs 405 nanometer laser light to the cuvette. We are capturing the fluorescence with the PMT, then we have a low noise amplifier, the constant fraction discriminator, and our film data acquisition card. So now I'm gonna use this setup to reconstruct a intensity decay profile of the fluorescence coming from the cuvette using TCSPC technique. You see that I am acquiring, using our spectroscopy software, the signal coming from the cuvette using a photomultiplier tube and a constant fraction discriminator. You see that I am reconstructing the intensity decay profile of fluorescence. This is what I wanted to show you today. So now we can stop the acquisition. Thank you for joining the webinar. So I'll post the video on YouTube for everybody to take a look. Thank you. Bye.